Section 6.2 Orbits. In this section, you'll learn how satellites move around the Earth and what determines their speed in space. You'll discover how gravity and motion work together to keep the satellite in orbit and how changing the satellite height affects how fast it travels. This section will also help you to understand why satellites don't fall back to Earth and how scientists calculate their orbital speed to keep them moving safely around the planet. You are already familiar to projectile motion and its range. Launching a satellite is in principle similar to the launching a projectile, but it requires much greater precision and speed. When a satellite is launched, it must reach a high enough velocity so as it falls toward Earth due to gravity, it also moves forward fast enough to continuously miss the Earth, effectively staying in orbit. This delicate balance between a satellite's forward motion and gravitational pull of the Earth keeps it moving in a stable path around the Earth. So it keeps missing the Earth and keep continuing circular motion. Let's look at the natural versus artificial satellites. A satellite is any object or a body that revolves around another body that is usually much larger in mass. Satellites can be natural or artificial. For example, planets are natural satellites that revolve around the sun. In a very similar way, moons, such as Earth moon, are natural satellites that orbit their respective planets. In our solar system, we have many moon-likes that are orbiting respective planets. Humans have created artificial satellites to orbit Earth for purpose of communication, GPS or any other cell phone communication, weather monitoring, and scientific research like an International Space Station. Planetary moons, including Earth moon, are natural satellites. As I mentioned, in addition to natural satellites, humans have created artificial satellites to orbit Earth for purpose like communication, weather monitoring, and scientific research like International Space Station that you see on that picture. Now let's look at the weightlessness fact or myth. It's a fact that astronauts feel weightless in orbit because they are in a constant free fall around the Earth. Myth is that gravity doesn't disappear in space. It is still strong enough to keep the spacecraft in orbit. Weightlessness is just a feeling of falling without hitting anything. So it's a constant free fall. Furthermore, artificial satellite is an object that has been intentionally placed by humans into the orbit around the Earth or another body, referred to as artificial to distinguish from natural satellites such as the Moon. For example, International Space Station is a spacecraft in which people live and work to conduct scientific experiments. Furthermore, International Space Station is a permanent orbiting laboratory that supports many different research projects that study human responses to the space travel and zero gravity or microgravity. At an altitude of International Space Station, the acceleration due to gravity or gravitational field strength, G, is still about 8.7 Newton per kilogram, which is strong. Why astronauts and everything else are feeling weightless? Astronauts aboard the International Space Station feel weightless not because the gravity is gone, but because the station and everything in it are in a constant state of free fall around the Earth. Isaac Newton proposed that the same force that pulls the object toward Earth that means it's a force of gravity, also keep the moon in its orbit around the Earth. This idea shows that the motion of the celestial bodies follow the same physical law as the objects on Earth. The orbital radius is the distance between the center of the satellite and the center of the body it orbits. For example, the moon orbital radius is the distance from the center of the moon to the center of the Earth. The force of gravity on the moon due to the Earth is a centripetal force that pulls the moon toward Earth's center. We talked about centripetal forces in chapter 3. As the moon orbits the Earth, it moves with a velocity that is perpendicular to a line connecting to the center of the Earth or tangent to that circular motion. This particular motion is what keeps the moon moving around the Earth rather than directly toward it. If there's no gravity, the moon will continue moving in a straight line and drift away into the space. If the moon had no orbital velocity, gravity would pull it straight down and causing it to fall toward the center of the Earth. The moon orbit exists because the balance between its forward motion and pull of the gravity. The moon orbit, like the orbit of the planets around the sun, is actually elliptical rather than a perfect circle. However, for most calculation and explanation, we can closely approximate these orbits as circular, which make it easier to understand and work with concepts like orbital speed and gravitational force. Gravitational acceleration is gm over r squared when me is the mass of the Earth. This is equal or must be equal to centripetal acceleration, which is v squared over r, based on chapter 3, uniform circular motion. So if they are together, from here you can solve for v, which is the square root of gm over r. The speed of the satellite depends on its orbital radius, and it is independent to the satellite mass. To maintain a stable orbit of the radius r, the satellite must travel at the constant speed, which is square root of gm over r. This speed ensures that the satellite forward motion balances the gravity pull trying to draw it toward the planet, keeping it in a smooth, continuously orbit. Let's compare and contrast two speed for a satellite, orbital speed versus escape speed. Artificial satellites can be launched from other planets as well. There's a list of the escape speed for planets and the moon. Escape speed is a minimum speed needed for an object to break free from the planet's gravity. Remember that orbiting speed and escape speed are not the same thing. Orbiting speed, we already talked about, that's a speed to keep the satellite in a stable, uniform circular motion in orbit. However, to get there from the surface of the planet to the stable satellite altitude, you need another formula, which is square root of 2gm over r. Remember, it's a square root of 2, which is a 1.44 times bigger than orbiting speed. Let's practice solving a problem involving orbiting. Two of the Saturn natural satellites, Prometeo and Pandora, have near circular orbits. They are located on a Saturn's F ring with a Prometheus on each side at 1.39 times 10 to the power of 8 meter from the Saturn, and Pandora on the outside at 1.42 times 10 to the power of 8 meter from Saturn. The mass of the Saturn is 5.68 times 10 to the power of 26 kilogram. Calculate the orbital speed of Prometheus and Pandora. Here are what are given to us. Make sure everything is in a standard unit. Gravitational constant is 6.67 times 10 to the power of negative 11. The formula for Prometheus is square root of GMS Saturn over R, or a distance from the center of the Saturn to a center of Prometheus. And if you plug those numbers in the calculator, you're going to get 1.65 times 10 to the power of 4 meters per second. The other one, Pandora, is very similar. The only change here is a RPA. That means the distance from the center of the Saturn to the center of that satellite or moon. If you plug those numbers in that calculator, you're going to see that the speed is 1.63 times 10 to the power of 4 meters per second, which is smaller because it's further away from the center of the Saturn. It is expected that way. The results prove it. A geosynchronous orbit is an orbit around the Earth in which a satellite orbital speed matches the Earth rotation. That means 24 hours. In this orbit, the satellite takes exactly 1 Earth day, so 24 hours, to complete the full orbit. As a result, the satellite appears to stay above the same point on Earth's surface, making this type of orbit especially useful for communication, weather, and surveillance satellites. A geostationary orbit is a special type of geosynchronous orbit in which the satellite travels directly above the Earth equator. In this orbit, the satellite motion matches the Earth rotation exactly, so to an observer on the ground, the satellite appears to be fixed over the same point in the sky at all times. One of the applications of the artificial satellites is for communication. How does the GPS work? The Global Positioning System, or GPS, determines the location of the object by coordinating signals from several satellites, typically a minimum of 3. The fourth one is used only for time. Using these signals, GPS can pinpoint the position on Earth's surface with an accuracy of 15 meters. Now, why do we need 3 or 4 satellites? If we only can use one satellite, the information it provides can only show that object is located somewhere along the circumference of the circle or the base of the cone that is formed between a satellite and the possibilities of where that location is. So that means it's not accurate. If one satellite wasn't not enough, what about 2 satellites? If 2 satellites are used, the data from both can be consulted simultaneously. This allows the position to be narrowed down to one of 2 possible points where the circles from each satellite intersect. But that's not accurate either. For this, we need a third one, when all 3 circles will intersect in one point, and that is the exact location on the Earth. Theoretically, this is done, but not enough, because what about travel time? The signal takes time to travel from satellite to receiver. For this one, we need the 4th satellite that is needed to adjust the position because of the signal travel delay. That is accurately done. If you want to learn more about how GPS works, follow this link. Let's do some practice problem. An artificial satellite, International Space Station in this case, orbits the Earth at an altitude of about 350 kilometers above Earth's surface. Mass and radius of the Earth are respectively 5.98 times 10 to the power of 24 kilogram and 6.38 times 10 to the power of 6 meter. Determine the speed needed by the International Space Station to maintain its orbit. Let's write what is given, what's required. Make sure all of them are standard units. We have mass of the Earth, radius of the Earth, altitude of the International Space Station. I wrote it as a 0.35 times 10 to the power of 6 on purpose to have the same exponent, 6. So when we add them together to make total distance from the center of the Earth to the center of the satellite, we'll make 6.73 times 10 to the power of 6 meter. Constant, gravitational constant, is 6.67 times 10 to the power of negative 11 Newton meter square over kilogram square. Speed is required. Let's write the formula. Make sure that you have everything as a standard unit. Plug those numbers in your calculator, and you're going to get 7.698 times 10 to the power of 3 meter per second, carrying a +1 sig fig from 3 to 4. Determine the orbital period of the International Space Station in minutes. Again, we are going to use the total 6.73 times 10 to the power of 6 meter as a total distance between center of the Earth and center of the satellite. Speed are we using from the previous calculation? We don't have choice here. We use calculated values. So period is 2 pi r total over v. So that means 2 pi times 6.73 times 10 to the power of 6 meter over 7.698 times 10 to the power of 3 meter per second. That will give you 5,493 seconds for sig figs. And then if you convert it to a minute, it's going to be 91.6 minutes, 3 sig figs, which you can see the International Space Station has a very high speed. So it orbits the Earth in almost 1.5 hours when the Earth is spinning around itself 24 hours. So you see how fast that International Space Station is moving. Here is another one. Astronomers have determined that a black hole sits at the center of the galaxy M87. Observations show matter at a distance of 5.34 times 10 to the power of 17 meter from the black hole and is traveling at the speed of 7.5 times 10 to the power of 5 meter per second. Calculate the mass of the black hole, assuming the matter being observed move in a circular orbit around it. So what do we have? We have a radius there, 5.34 times 10 to the power of 17 meter. The speed is 7.5 times 10 to the power of 5 meter per second. Mass is required. Then formula itself is from V equals square root of gm over r. We solve for r. That is going to be v squared r over g. Then we have everything here as a standard unit. Plug those numbers in the calculator, and you're going to have 4.5 times 10 to the power of 39 kilogram, or 4.50 times 10 to the power of 39 kilogram. Let's do another problem. Mars orbits the Sun in a nearly circular orbit of radius 2.28 times 10 to the power of 11 meter. The mass of the Mars is 6.42 times 10 to the power of 23 kilogram. Mars experiences a gravitational force from Sun of the magnitude of 1.63 times 10 to the power of 21 Newton. Calculate the speed of the Mars and the period of revolution for Mars in terms of Earth years. So here's what is given. The distance between center of the mass to center of the Sun, 2.28 times 10 to the power of 11 meter. Mars mass is 6.42 times 10 to the power of 23 kilogram. Force between Mars and Sun, 1.63 times 10 to the power of 21 Newton. Speed and the period are required. In order to find speed, we need to find mass of the Sun. because sun is in the center. That makes the Mars to orbit the sun. So from the force, which is gmm over r squared, you solve for mass of the sun, which is r squared times force divided by g times mass of the Mars. Everything is a standard unit, and you'll find 1.98 times 10 to the power of 30 kilogram. Now, we are ready to find speed, which is square root of gm over r. From here, speed is 6.67 times 10 to the power of negative 11 times 1.98 times 10 to the power of 30 kilogram divided by 2.28 times 10 to the power of 11 meter. When you plug that in the calculator, you'll get 2.41 times 10 to the power of 4 meter per second. So by getting the speed, you can look at the period of revolution. So one cycle, that means the circumference of this orbiting, is 2 pi r over v. Plug those numbers, all are standard units, and you get 59,442,583 seconds. If you convert into years, the Earth years, remember they are 365 days, 24 hours in a day, and 3,600 in 1 hour. If you divide that number with all those numbers that I mentioned, divided by 365, divided by 24, divided by 3,600, you'll get 1.88 Earth years. Here is another problem. Calculate the speed of the satellite in a circular orbit 600 kilometers above Earth's surface. Determine the orbital period of the satellite. Use mass and radius from previous problem. Now, mass of the Earth, 5.98 times 10 to the power of 24 kilogram. Radius, 6.38 times 10 to the power of 6 meter. Altitude of the satellite is 600 kilometers, or 6 times 10 to the power of 5 meter. The universal constant is 6.67 times 10 to the power of negative 11 Newton, meter square, kilogram square. Speed and period are required. Let's start with speed first. Square root of gm over r, in this case, is the total r of radius of the Earth and altitude. Everything is in standard unit. You plug that in a calculator and you'll get 7.56 times 10 to the power of 3 meter per second. From here, the same way, we're going to do period, 2 pi r over v. R is total of RE and HS. That means altitude and radius of the Earth. Plug those numbers in the calculator and you'll get 5,820 seconds. Here is another video that I recommend to watch. The link will be posted. Another video that I recommend to watch. The link will be posted as well. Moving in space has been dream of all scientists. And in this section, we're going to explore how can we use force of attraction, force of gravity, in order to jump from one planet sphere or a gravitational attraction to another one in order to explore the universe without using a lot of energy. No matter how advanced we build a spaceship, it always will have a limited capacity for fuel. So how can we explore the solar system, or actually space, without running out of fuel? The gravitational fields of the planet can be used to guide and adjust the path of the space probes. By carefully planning the probe's trajectory, scientists can use the gravity of the planets as a slingshot or to accelerate the spacecraft by changing its speed and direction without using extra fuel. This technique, known as a gravity assist, allows probes to reach distant destinations more efficiently by jumping from one gravitational field of the planet to another gravitational field of the planet, and that way we move away from Earth to explore the universe. The German astronomer Johannes Kepler came up with three laws. The first one states that all planets move in an elliptical orbit around the Sun. In each orbit, Sun is located in one focus of the ellipse, while the second one is empty. This means that the planet distance from Sun changes as it moves along to the orbit. Sometimes it's closer, sometimes it's further away. This diagram that you see, it's a little bit exaggerated. The focal point actually are not that far apart. They are very close together, so the ellipse is closer to a circle. Kepler's second law states that an imaginary line drawn from a sun to a planet sweeps out equal areas in equal times. This means that the planet moves faster when it is closer to the sun and is slower when it's further away. For example, the areas swept out from 1 to 2 and 3 to 4 are equal, even though the planets cover different distances along its orbit in the same amount of time. Look at the diagram on the right. If you see that area A1 is equal to area A2, in order for A1 to be equal to A2, the distance that covers from point 1 to point 2 has to be longer for same amount of time. Delta T1 is equal to delta T2. As a result, that planet from point 1 to point 2 has to move faster to cover the bigger distance for the same interval of time compared to 3 to 4 when it moves slower for the same amount of time and covers small distance in order for area to be equal. As you might have noticed already, first and second Kepler's law are descriptive, while the third one is mathematical. The square of the orbital period of any planet is proportional to a cube of the average distance from Sun to the planet. Now, universal gravitational force, as you know, is a centripetal force that keeps the planets in the orbit. Centripetal acceleration is equal to 4 pi square r over t squared. As we rearrange this equation for t squared, we get t squared is equal to 4 pi square over gm times r in the power of 3. This is mathematical representation of Kepler's third law. Now, as you know, t is a period of planet and r is a distance from planet to sun, or the length of the semi-major axis of the ellipse. Now, look at the formula itself. The portion 4 pi square over gm is constant. Everything there is constant for our solar system. So for this one, we label it as a k, and we change that third Kepler's law as t squared is equal to k times r in the power of 3. This k, this constant for a solar system is 2.97 times 10 to the power of negative 19 second squared over cubic meter. So k is independent of the mass of the planet. Let's solve some problems. Calculate the mass of the sun, noting that period of Earth orbiting the sun is 3.156 times 10 to the power of 7 seconds, and its distance r from the sun is 1.496 times 10 to the power of 11 meter. So distance and period are given. Mass of the sun is required. Look at the formula, and we solve for m. M is equal to 4 pi square r cubic divided by gt squared. Plug numbers, all of them are standard units, and you'll get 1.989 times 10 to the power of 30 kilogram. 2. It is needed for a telecommunication satellites to remain in the same location relative to location on the Earth. This can occur only if the satellite orbital period is the same as the Earth period of rotation, 24 hours. So what is the orbital period of satellite? 24 hours, or 86,400 seconds. Let's continue with B. At what distance from the center of the Earth can this geosynchronous orbit be found? So we have a period that we already calculated. The mass of the Earth is given 5.97 times 10 to the power of 24. The distance is required. So using a third Kepler's law, this time we solve for r. And r is equal gm times t squared over 4 pi squared. All this in the power of 1/3. Plug those numbers, all of them are standard units, and you get 42,226,910 meter, or in a kilometer, 42,230 kilometers. This is a summary of section 6.2 orbits, and practically is the end of the chapter. Please do your homework and prepare for chapter test.